In this video, we are going to solve problem based on pressure, hydraulic lift, and Pascal principle. Question 36. An automobile weighing 2.3 times 10 to the power 4 Newton is lifted by a hydraulic cylinder with an area of 0.15 meters squared. Part A of the question is asking you what is the pressure in the hydraulic cylinder. So let us first write down what the question has given us. We have the weight of the automobile, which is nothing but the force due to gravity acting on the object. So I will write this as my force F to be equal to 2.3 times 10 to the power 4 Newton. Then we have the area of the cylinder. So area A is 0.15 meter squared. In part A, we need to find what is the pressure in the hydraulic cylinder. So we need to find what is the pressure P. We know that pressure P is equal to force over the area. I have the force and the area. We will just substitute to solve this. Force F is 2.3 times 10 to the power 4 Newton over 0.15 meters squared is the area. And when you solve this, you get the pressure exerted to be 15333 Pascal, which you can write as 1.53 times 10 to the power 5 Pascal. Then in part B, they are asking you the pressure in the lifting cylinder is produced by pushing a 0.0082 meter square cylinder. What force must be exerted on this small cylinder to lift the automobile? So in part B, we have two different area. Area 1 is the area of the cylinder we considered before, which is 0.15 meters squared. Then area 2 of the lifting cylinder, which is 0.0082 meters squared. Then we have force 1, which was the weight of the automobile, which is 2.3 times 10 to the power 4 Newton. We need to find force F2 that must be exerted on the small cylinder. To find this, we are going to use the formula for hydraulic lift, which is F2 equals F1 A2 over A1. You can get this rule for hydraulic lift by using Pascal's principle, which says that change in pressure in one region is equal to the change in pressure in another if you have a liquid which is confined. So pressure in one region can be written as F1 over A1. In the other, you can write it as F2 over A2. And when you multiply with A2 on both sides, you get F2 to be equal to F1 A2 over A1. So you can arrive at this rule by using either Pascal's principle or just directly using the formula for hydraulic lift. So let's solve. I have F1 equals 2.3 times 10 to the power 4. Area 2 is 0.0082 over area 1 is 0.15. Then when you solve this, you get F2 as 1257.3 Newton, which you can write as 1.257 times 10 to the power 3 Newton, or round it off to 1.3 times 10 to the power 3 Newton. This is the force that must be exerted on the small cylinder to lift the automobile. Question 105. Auto maintenance. A hydraulic jack is used to lift cars for repair is called a 3-ton jack. A large piston is 22 mm in diameter and the small one is 6.3 mm in diameter. Assume that a force of 3 ton is 3 times 10 to the power 4 Newton. First part of the question is asking you, what force must be exerted on the small piston to lift a 3-ton weight? So I will write the given quantities. I have the force F1, which is the weight of the object to be lifted, which is 3 ton. And they have mentioned 3 ton is equivalent to 3.0 times 10 to the power 4 Newton. Then I have the diameter of the large piston, which I will call D1, to be equal to 22 millimeter. This diameter I will convert to radius R1, we know the radius is half of the diameter, so that will give me 22 by 2, which is 11 millimeter. Then I have the diameter of the smaller piston, I will call it D2, which is equal to 6.3 millimeter. I will find radius of this piston as R2, which is D2 by 2. That will be 6.3 divided by 2, and that's equal to 3.15 millimeter. I need to find what is the force exerted on the small piston to lift a 3-ton weight. So I need to find what is the force F2. Again, we are going to use the equation for hydraulic lift, which was F2 equals F1 A2 over A1. Now the surface area of a piston is circular with a radius R. And if you want to find the surface area of the piston, we need to find the area of this circular region. And area of a circle is equal to pi r squared. So here for area A2 and A1, I'm going to substitute pi r squared, taking the corresponding radii of the piston. So we rewrite the expression as F2 equals F1. Area 2 I will write as pi r2 squared over area 1 will be pi r1 squared. Then you can cancel off the pi from the numerator and denominator, and I'm left with F2 equals F1 R2 squared over R1 squared. Now substitute. F1 is 3 times 10 to the power 4. R2 is 3.15 millimeter squared. R1 is 11 millimeter squared. And when you solve, you get F2 to be equal to 2460 Newton, which you can write as 2.46 times 10 to the power 3 Newton, or just round it off to 2.5 times 10 to the power 3 Newton. Part B of the question says, most jack use a lever to reduce force needed on a small piston. If the resistance arm is 3 centimeter, how long must be the effort arm of an ideal lever be to reduce the force to 100 Newton? In part A, in order to lift a weight of 3 ton, we had to apply a force of 2.5 times 10 to the power 3 Newton. Now to reduce this force, we are going to use a lever in part B, an ideal lever. So this becomes my resistance force, as this is the amount of force I want to overcome. And I want to reduce this force to a force of 100 Newton. So this becomes my effort force, 100 Newton. I should be able to apply only 100 Newton to lift a weight of 2.5 times 10 to the power 3 Newton. So if the length of the resistance arm, which is LR, equals 3 centimeter, what should be the length of the effort arm? Now for an ideal lever, in order for us to lift this weight, the torque exerted by the effort arm must be equal to the torque exerted by the resistance arm. Now torque is given as force times the distance, and for us the distance is the length of the arm, which is L. So I will write this as torque exerted by the effort arm to be force exerted by the effort arm times its length equals force of the resistance arm times its length. I need to find the length of the effort arm, so we divide by this force Fe on both sides. I get Le equals Fr Lr over Fe. If you do not want to rearrange like this, you can just use shift solve at this point over here. Substitute the values of Fe, Fr, and Lr and shift solve to get Le. So now we substitute resistance force, or the force of the resistance arm, is 2.5 times 10 to the power 3. Length of the resistance arm is 3 centimeter. Force on the effort arm, we only want to apply a force of 100 Newton. Now solve for this, you get the length of the effort arm to be 75 centimeter. Since the unit of length here we took it as centimeter, the final answer will also be in centimeter. So this is how long the effort arm should be in order to reduce our force from 2.5 times 10 to the power 3 Newton to 100 Newton.